Good morning, everybody. Get all my stuff in order here. Happy Cinco de Mayo. I don't have any way of celebrating that, and it makes me sad. Good morning. Okay, I'm gonna get started because I keep remembering that you can pause me. Okay, so today we're learning about, I called this lesson Elements of Probability just because there's no real name for all of this stuff combined. So basically, it's just these are some extra things that happen sometimes in probability, and we're going to talk about how they affect probability and how you can calculate probability. So the first thing that I wanted to talk about is the fundamental counting principle. Yeah. So when you have, so this first little piece says sample space, goodness, sorry, I haven't talked yet today. Sample space can sometimes be tricky to calculate when you are considering multiple events. When this is the case, you can use this rule. So, so this is for when you have several options in several different parts, which doesn't make a lot of sense until you see examples. But this is super important, like note card stuff. When there are m outcomes for one event and n outcomes for another, there are m times n outcomes for both. So we're just going to talk about this car thing first. And I know that the color thing doesn't really help because your and my books are in black and white. So we're going to have to just trust that that's black and red and green. So here's the deal. Greg goes to buy a new car and he's given these kinds of options here. He is given 2 different body styles. How many colors is that? 5 colors and 3 models. So forgive me while I draw a giant picture here because I just want to show you that this ends up giving you a lot of different potential cars that he could buy. So we have 2 different models. That's like the first option he's given. Here's my really good drawing. I'm an artist. He has, what do they call them? Thanks. I don't know. I can't remember what the 2 kinds of cars were called from this problem, but that's okay. So we have 2 different models, and then for each of those models, we have 5 different colors. So he could buy a black one, a red one, a green one, a blue one, and a silver one. I'm most definitely going to run out of room. That's okay though. Black, red, green, blue, silver. Same for this model. Black, red, green, blue, silver. And for each of those colors, he could buy 3 different models. So our tree is going to look a lot more exciting here. I did also remember that a lot of your math base has like these probability trees, and we didn't really talk about how to do those. So I don't know if I can't remember if they were on your first homework assignment, but I apologize for that. I will remind me. I need to talk about that today. But essentially, probability trees look very much like this. Like you're given a certain number of events, and for each event, different things can happen. So for this one, we have 2 different, the probability tree would start in the middle, and then you have 2 different models. Wait, not models, body styles, 2 different styles, 5 different colors for each of those, and then 3 different models for each of those. So we have GL, SS, and SL for each of these. So you might be thinking to yourself, this is a lot of work, and I wish there was an easier way to do this. And you're right. I know this is really messy and you can't read it, but you know what's going on. I'm just putting each of these options, GL, SS, and SL, for each color. GL. Maybe I'll zoom in, that would help. SS, and SL. And the same thing happens over here. Forgive me if I don't actually fill in all of these things. There are 3 different models for each of these colors. The same models. And ... because I don't want to keep going. So once you have made this probability tree, you can calculate probabilities, which is nice. That's what probability trees are nice for. But you can also see the potential sample space, how many different outcomes there could be in this situation. Each of these endpoints represents a specific kind of car, so a specific body style, a specific color, and then a specific model. And in total, there are 30 options. And you know what? The easier way to do this, that I mentioned 5 minutes ago, is that you, instead of having to make all of these diagrams, you can very quickly figure out how many outcomes there are when you have several different options like this, by just multiplying how many options you have for each choice. Hopefully that translates. So here we have 2 options for the style, the body style. We have 5 options for the color and 3 options for the model. And you might notice that 2 times 5 times 3 gives you 30. And that is the much simpler way to do these problems. Just multiply how many options you have for each choice. You just multiply them all together. No matter how many different choices they're giving you. For example, if like this car also had, like, you could pick different door styles or like different seat coverings, or like any of those options, you could just tack them on the end and multiply all of those, the number of options you have for each choice. So we have a couple of example problems here, which are harder to make up than they are to solve. Number 1, if you spin 2 spinners, one with 10 letters and the other with 3 numbers, how many outcomes could there be? So we have 10 options for the first, 10 outcomes for the first, the spinner, and 3 outcomes for the numbers. And all we have to do is just multiply those two things together. We multiply the 10 options times the 3 options, and it gives us 30. And each of those represents a unique outcome on the spinner and they're both spinners, so they're both spinners. If you roll a 20-sided die and then a 100-sided die, how many outcomes could there be? As you might imagine, a lot. Because for each of those, anyway, 100-sided die has a lot of options. But the mathematical way, we just multiply both of these number of options together and we get 2,000 different outcomes on both die, if you're rolling both die. So for example, rolling a 2 and a 50, a 2 on the first die and a 50 on the second die, is a different one than rolling a 2 and a 4 on the second sided die. So they're representing sort of one outcome together. Number 3, Olivia is building her own pizza at her favorite pizza place. There are 2 different types of crusts. Okay, I'm going to start writing these while I'm reading. There are 2 different types of crusts, 2 different sauces, and 4 different toppings. If she's looking to try something new and has tried 6 different pizzas already, how many new pizzas are there for her to try? So first of all, we need to figure out how many total pizzas are possible with this menu. Which is just the total of these all multiplied together, which is 16. And she says she's already tried 6 different pizzas. So and it's asking how many new pizzas are there for her to try, meaning that we're just taking away 6 from the total number of total possible pizzas, which leaves us with 10. I don't know if you can read that. I can't read that. Hang on. There are 10 left. Okay. Okay, so not too bad. I assume that you can probably figure that one out. We're going to move on to a different different element of probability, if you will. We're going to talk about or and. In math, or and mean very specific things. Like in English, we use them, and you will probably think of several different ways that we use them as we talk about this. So in math, or, when we say or, this is the first bit. When we say or in math, such as when we say event A or B, it means that what we mean is that either A happens, B happens, or both. So we're thinking of this in terms of favorable outcomes. So if we're saying it's favorable for A or B to happen in math, we mean that if A happens, it's good. If B happens, it's good. And if both A and B happen, it's also great. So any of those things work out great for us. That's our favorable outcomes. So we're going to introduce the idea of these Venn diagrams, and usually I know that you've seen Venn diagrams in many different contexts. These Venn diagrams are relatively simple. One circle, such as this circle, represents event A happening, and this circle represents event B happening. So in this box, in this little piece of the circle, right, that means that only A is happening. In this part, let's outline it with my fancy, there you go. Like this portion of the Venn diagram represents only B happening. And again, this part represents only A happening. And as you might imagine, go away. This almond shape in the middle is when both A and B happen. So we're highlighting these Venn diagrams to show which part is our favorable outcome. And we're saying that it's favorable for A or B. A or B is favorable. So if A happens, great. If they both happen, awesome. Or if just event B happens, also great. So that whole part that we highlighted on the Venn diagram are all favorable outcomes. You might think that's the whole thing, which you're kind of right, except for what we didn't highlight is this outside of the Venn diagram and inside the box part. That part represents neither of those events happening. So like if event A is riding a horse and B is falling off the horse, outside of those two circles is not riding a horse or falling off a horse at all, right? It's neither of those things happening. So we did not highlight that part because that's not favorable. We said A or B is favorable, not neither. So sorry if that's too much explanation for something. I just want to make sure. I never know. I hate teaching online. I'm sorry. I'm sure you guys hate learning online, but it's good. It's fine. We're surviving. And let's talk about and. So the word and in math contexts, when we say like A and B is favorable, we want both to happen and only both. That's the only acceptable option. So both A and B happen. So here's the part where English and math contexts kind of diverge, right? So like if we were to say in a sentence that like say like what's two things happening? Um like having pizza for lunch and getting to play video games. So in English we could say like, hey, it would be awesome if I got to eat pizza and play video games, right? And it could mean that one of those things is awesome and the other thing is awesome, and so is both. But in math, both of them need to happen. Like, there's no acceptable situation where only one happens. We're saying that and means that both happen, right? English sometimes can like make it a little bit, there's like a little bit of wiggle room in English. Math, we have to just get rid of that wiggle room. Um, so the only favorable option is if both event A and event B occur, which is just the intersecting part of those circles. So very much less than our or option. So now we have and or. Um, I think these Venn diagram things are kind of fun. I don't know. I wish I could give you homework just these Venn diagrams. I'm sure you would hate me. But I think they're really fun to sort of theoretically think about because I probably said this before. The reason I like math is because there is not wiggle room, right? If you the right answer is always going to be right, even in 100 years. And 100 years ago, the right answer is always right, which is something I appreciate about math. Of course, anyway, yeah. So, reading English sentences and deciding what they mean in exact terms is kind of fun to me. So forgive me for having too much fun with these. Don't worry, there's like one or two of these on MathSpace in existence, so I really couldn't give you all of your homework on this. But anyhow, so what we're doing with these things is where each of these circles represents different events A, B, and C. And again, outside of the circles, but inside that square is like when none of those events happen. So we're reading this sentence that it gives us, and we're deciding where on our what events or like what part of the Venn diagram we're talking about with that sentence. So, for example, I hope I can walk you through my thinking on this one because I know this is like weird, new, and yeah, it's very specific kind of thinking. So, this one says events A and B, but not C. So, remember that and means that the only favorable thing here is that both A and B are happening, right? So, if we just had this portion of this sentence, A and B, we would highlight only this almond shape, right? Um, because both A and B are occurring. That's our A and B. However, we've added here, but not C. So there's a portion of this almond shape that is now not favorable because C is happening. We only want A and B, right? Both of them occurring, but if C happens, we're no longer happy. So we now need to take away this portion that's inside of the C circle because that's where C is occurring. So that not C becomes um, relevant here, right? So we have A and B, but then not C. We took away the little part that was in C's circle. There you go. Okay, let's try more of these. If this is like, hey, I kind of get this, pause me and try the rest of these because I think they're kind of fun to think about. Um, yeah, and they're more fun when I'm not just telling you the answer. So pause me. Okay, for this next one, events A or B or C is what we're looking for. So remember that or in math means it's fine if one happens, it's fine if the other happens, and it's also fine if both of them happen. And in this context, we have three ors, or two ors, I guess. Yeah, but we have three events, and we are good if any of those events happen, or if all of those events happen, or if any combination of two of them happen. So that's what or is meaning in this context. So as you might have guessed, we're just going to like highlight, ooh, big highlighter, everything inside of the circles. Because all of that is fine and dandy with or. As long as one of those things is happening, we're good. The only unfavorable thing we have is for none of them to happen. It's also kind of fun to think about. These Venn diagrams help you think about what the inverse or what the opposite of this would be. Like the opposite of A or B or C would be none of the events happening, right? Just something to think about. This is like something you might encounter if you end up doing math in college. You talk about truth statements and like inverses and converses, and I really enjoyed that class and that subject, which might be why I like this stuff. But it comes up a lot in probability, which is why we're talking about it, because it's important to understand what mathematically these things mean. But they're also really fun to play around with just by themselves, like truth statements and true and false and stuff like that, with actual statements that are not just like A, B, and C. So something interesting. Events A and B or C. So, okay, first of all, A and B, yikes. A and B is this almond shape. Both of them are happening. But then it says or C, and or means that it's good if C happens, right? And it's also good if A and B happen. So we have an or statement that adds all of this C in here, because C is also favorable because of that or statement. So we basically, the or separates this little bit and the A and B, and so we're saying A and B is good, or C is good, or both of them happening is good, right? And so instead of having just one event or another event, we're having like a pair of events happening with an and statement or another event. Events A and B and C. Remember, and is restrictive, right? So and means that both of them have to happen. And in this case, all of them have to happen, right? A and B and C has to occur. None of just pairs of two or one is good, right? Which means that the only thing we're highlighting in this case is just this middle. That's not a highlighter. It's fine now. Just that middle like triangle shape, because that's where all three events are happening. And now we get into some knots down here. None of and knots. So this one says none of A, B, or C. So kind of like we talked about in number 2, this is the opposite of that, right? We're saying none of these events are occurring, not one of them, not all of them, not any two of them, none of them, right? And in this case, the only favorable part of this Venn diagram is the outside square. Anything happening is fine as long as it's not A, B, or C. So this is the exact opposite of the second statement we looked at. And number 6, this one just says not event A. So anything happening is great unless it's event A. So this one, everything is fine as long as it's not A, right? is going to be messy, but you get my idea, right? Not event A, is just everything besides event A. Yes. So you'll see Venn diagrams, I think, on your homework today or maybe next time, where they have Venn diagrams that are they're not just like events. They're also, they've got numbers in there. So they might say like, let me just write in here. They might say that like 10 people or 10 times only event A happened. Like people like, I don't know what starts with A. Apples. 10 people like apples. Like 2 people like apples and chocolate, but not bananas. I'm making this up as I go. 1 person likes apples, chocolate, and bananas. That's me. I'm in the middle. Like 5 people just like chocolate and none of the other things. And you see what I'm saying? So they'll fill in like numbers here. For each of these parts, and you can use them to find probabilities. So you can even say like 15 people don't like any of those things at all. And I don't know how many people like bananas. 6? There you go. Just bananas and not apples and chocolate. So do you see how you can figure out probabilities? So like you could ask like what's the probability somebody only likes apples and not none of the other things. And out of the total number, you'd have to add all those people together. Only 10 out of whatever that total number is. So you might see that today. I will be holding a study session today, probably at 11, I imagine. So just watch Google Hangouts for that link. I'd be happy to help you with today's or yesterday's homework. Because I mean, I know that there were some there's like probability trees, which are something we didn't talk about. I forgot to do that. So anyway, join me on my study session. So we have one more thing to talk about, and this is kind of an interesting thing. Some people really like to think about dependence and independence. And it's really actually a very big topic in probability because it comes up a lot and it greatly affects the probability math that we do, whether or not 2 things are dependent or independent. So 2 events are dependent, meaning, yes, they're dependent if the probability of one affects the probability of the other. So, for example, I have to think of something that's dependent. Surprisingly, the dependent ones are not as common as the independent ones because independent probabilities are easier to calculate. Dependent ones are harder because they change each other essentially. So like you might be able to think of better examples, but like for the sake of we're gonna go with food because that's for some reason what I'm thinking about. Okay, so let's just say the probability of someone liking like any kind of noodles, right? Don't judge me for my examples. And the probability of somebody liking spaghetti specifically. Or something else made out of noodles. Yeah, I'm gonna go with spaghetti because I like spaghetti. Try to think of a better example for your notes because that's a terrible example. But you know, for example, if somebody hates noodles, they're probably not gonna like spaghetti, right? So the probability affects each other. They like depend on one another. And you would be surprised the amount of people in the world dedicated to figuring out if things depend on each other. So this is like a huge industry for advertising and for just probability like studies, scientific studies in general, trying to figure out if the things depend on one another when we're not sure. Um, things that might be controversial, and we'll talk about a couple of them down below here. But I think one of the things that I have here is um, like a person's yeah, okay. So number 10 on this page says a person's political party after age 20 and their parents' political party. So that's something that you would wonder, for example, it probably is dependent, right? But in what way is it dependent? Because some people, after they leave their parents' house, are like, okay, that was not what I thought. And other people just sort of stick with tradition and end up being the same political party as their parents. So anyway, that's something interesting to think about. People dedicate their lives to studying these sort of things, whether or not things are dependent or independent. So some things are very clearly not dependent, especially random chance type of things. But real life things are really hard to tell if they're dependent. For example, like somebody's gender identity and the kind of car they drive, or like you know what I mean? There's just all sorts of things that you could never know unless you spend a lot of time studying it and calculating probabilities. So, anyway, that's my spiel. Let's talk about independence now. So this is obviously the opposite. The probability of one does not affect probability. It's a long word to spell 100 times. Probability of the other. So sometimes we joke there's going to be a lot of examples of independence in our examples down below. So I won't add an example because you can probably imagine what kinds of examples there are. But sometimes with independent events, we as humans are very good at finding patterns where there are no patterns. That's why stereotypes exist. That's why um, people think that they're cursed and all sorts of things. Like in when there's really no patterns, people like to find patterns. So for example, if you're playing a board game and you keep rolling super low on the dice, you're like, okay, like obviously the next roll is probably going to be low too, right? Because you get in this groove and you think that's just how you're rolling today or whatever. The fates have combined against you. Um, when really the probability of one dice roll does not affect the next dice roll at all. Like every time you roll the dice, it could be it's completely independent of the last time you rolled the dice, or who's holding the dice, or who like wished you luck. You know what I mean? Those things are totally independent. So that's something that's interesting. People often like to find independence when there is no dependence in probability. Um, something interesting about human behavior. So let's talk about some examples. Most of these, again, are going to be independent because it's hard to think of dependent examples. But yeah, really. Um, so number one, spinning two spinners, both with letters on them, getting A and then F. Definitely independent. Spinners are another random probability thing. Theoretically, they are supposed to be completely random. Number two, pulling a green marble out of an assorted bag and then pulling another green marble out of the same bag. So this one is interesting because you would think drawing a marble out of a bag is a random event, right? However, if you have, say, a bag of marbles with a bunch of different colors mixed, and you draw out a green marble, then the next time you dip your hand in, the probability is different of getting a green marble, right? Because you have just lowered the probability by taking out a green marble. Hopefully that makes sense. Because there used to be one more green marble, so the probability was higher the first time you drew a marble. So those two things actually depend on one another. If you were to replace the green marble, then it would become independent. Then they are no longer dependent on one another, and the probabilities are exactly the same anytime you stick your hand in there and try to pull out a marble, right? So this is actually a dependent example. Those two things depend on one another if you don't replace the marble. If there was like a little subnote here that said the marble was replaced in between, then it would become independent completely. Number 3, drawing a queen from a deck of a shuffled cards, replacing the queen, shuffling the deck, and then drawing a king. So drawing cards is also a random event, and in this case, we have replaced the card that we started with. And in fact, if you drew out a queen, anyway, yeah, no, never mind. You're replacing the card, right? So that is an independent event. It doesn't matter, like the second time that you draw a card isn't any less or more. It's not any less or more probable that you get one thing over another. So that is independent. Next, rolling a 20-sided die and getting a 5, and throwing a dart at a dartboard and hitting the center. Obviously, they're not even related. These are independent events. The probability of one does not affect the other one. Number 5, rolling a high number on a 20-sided die and then rolling another high number. Remember when I said I was a nerd? This is another thing. People are often, when they play D&D, like, oh no, I'm just rolling terrible tonight, which is such a funny statement because anytime you roll the die, it's completely independent of the last time you roll it. But anyway, this person's having good luck, rolling a high number on a 20-sided die and rolling another high number. Those things are completely independent of each other, and the same probability occurred when you first rolled it as the second time, so that is independent. Number 6, getting chosen in a raffle and then your friend winning right afterwards. And then it says they do not replace the names of those chosen. This is another one where because it's not replacing, they're not replacing the people chosen. The probability of your friend getting chosen after you got chosen is actually different, right? So I could actually genuinely I could argue both ways on this one. So if you think it's the other way around, if it doesn't matter if you got chosen, like as long as somebody got chosen, then the probability of the friend is the same. I don't know. Anyway, so I will actually leave that one up to you. I'm gonna put independent like slash dependent. If we were in class, we would have a debate about this and see if which one won, but a lot of these are speculative. We don't really know unless we do a study, and it depends on all sorts of different circumstances that are happening, which is why we have this speculative, this is like thing at the bottom, where these things I genuinely have no idea, and you would not really know either, but we all have sort of opinions about whether or not we think it's dependent or not. Um, even though we don't like stereotypes and we don't like to judge people based on certain things, they exist for a reason, right? So like number 7, for example, like um like whether or not we like to believe it, dudes drive trucks more often than female, right? People do. So I don't know. So this is like again, this is speculative. So in my opinion, I would think that it is a little bit dependent, even if it's a tiny bit. I love driving trucks personally, so but I don't. I don't own a truck. I wish I did. It'd be a lot easier to like haul like lumber. Don't ask me why I'm hauling lumber, but anyway, I have a lot of projects and I would wish I drove a truck, but I don't. So anyway, then there's things like eye color and profession. Are those actually dependent or are they independent? Like even though those don't seem to have any effect on each other, like maybe they do. Like, if you did a study of all the people and their professions and their eye colors, would one be dependent on the other? I don't know. Personally, I think no. I think that it probably would not be dependent. I'm leaving these blank because I want you to put your own ideas on here. But number 9, a person's height and their grade in high school math. I don't know. We need to know everyone's height, and then we can do a study. That one I would guess it's independent. I don't think height and grade in math is actually related, but who knows? And again, we already sort of talked about this one, but a person's political party after age 20 and their parents' political party. Interesting to think about. I think that would be dependent, but it may not be. It may be that so much so that, like, I don't know, it might be half and half kind of a thing where it just sort of balances each other out and there's no dependence. I don't know, I still think it's dependent. So I'm leaving those blank. Fill in whatever you want. And literally, no one's going to judge you. It's just speculation, obviously. So you're allowed to judge me. You can judge me and my opinions, but not each other. Um, yeah. So I'm gonna let you think about that really quick. I'm gonna pull up a question on MathSpace with a probability tree, and we're gonna do an example because I forgot to do that last time. So I'm gonna give you a second and just hang on. I will pull up question and I will tell you which one it is, and we will do it. If you're already done too, what you can do is try to think of an events that are dependent, that you think are dependent. Um, Things like how much time people spend on social media and whether or not they're on medication for mental illness, like things that are super controversial, uh, are sometimes interesting to think about. Like, are those dependent or are they not? Okay. Sorry, I'm trying to find a question. Maybe there weren't any? How many color options? Standard six-sided die is rolled. Okay, maybe there weren't any on last night's homework. I retract my apology. If you remember questions, tell me what number and I will find them. But I know there are some on tonight's homework, so I'm gonna pull up one of those. There's some Venn diagrams and maybe I lied. Okay. Maybe I'm a better teacher than I thought and I put them on later lessons. This is the problem with being prepared too soon. You forget what you did. It was too long ago. Oh yeah, it's on 10-3. One of them is. Okay. Yeah. Okay. We're gonna do that next time then because it's on 10-3 homework and not 10-2, so we're good. I retract my apology fully, and I will talk about that when we get to it on 10-3. So, okay. that's all I have for you. Enjoy May 5th. Um, yeah. Again, watch Google Hangouts for the study session, and I will hopefully see you then. Have a good rest of your day.